So we get started. This is the last class for the representation theory course. And I don't know whether you had a chance to think about this articulated exercise that we left about the character table of A5. However, I was thinking to go through the questions in order. If you have questions, also you can ask on the way. So the purpose is to write the character table of A5. So now I start writing the matrix that we have to fill. So we have A5. A5 is a group with 60 elements and 5 conjugacy classes. So we expect we have to construct the characters of 5 distinct representations. So now I start writing. Okay. So we have the equivalence class of 1. I try to use the same order and same notation as in the exercise sheet, the text. So 1, then we have the 2 cycles, 1, 2, 3, 4, 3 cycles, 1, 2, 3. Then we have the 5 cycles, 1, 2, 3, 4, 5, and the equivalence class of another cycle. 5 cycle is, actually I know, is 1, 3, 4, 2, 5. So okay, these are the representatives of the 5 conjugacy classes. And here we will write the characters. So as usual, we have the trivial representation. Every group has it. So chi1 will be 1, 1, 1, 1, 1. Then another representation that we know for A5 is the restriction to A5 of the permutation representations or representation of S5 permuting the basis elements in C5. And we know that that representation is 4-dimensional, right? So A5 acts on C5 permuting coordinates, and we know that C5 is V0 plus span all elements with same coordinates, and this is an invariant, irreducible invariant subspace of dimension 4. And V0 is exactly the hyperplane whose coordinates sum to 0. So the character table for this representation, which is called here rho 4, is 4. Here we have the dimension. Then we have, on the 2 cycles, we have the trace of the matrix would be 1, but we have to remove the contribution from this, so it is 0. 0. On the 3 cycles, it is 2 minus 1. No? The first 3 elements are moved. 2 are fixed, we remove the contribution, so it is 1. And on the 5 cycles, it is actually minus 1. No? When we look at the matrix of this kind of permutations, we find zeros on the diagonal, but then we have to remove the character of the trivial representation on span of 1, 1, 1, 1. So minus 1 here and minus 1 here. Now we have a few more to construct, which are called rho 5, rho 3, and rho 3 prime. And we will fill this table using all the properties of the character table that we have seen so far. Actually, a few more tricks with respect to the last exercise session. So, in fact, here we answered more or less to the first question about the conjugacy classes. You know, all the 3 cycles in A5 fall into the same conjugacy class. In fact, you know, the possibilities, of course, in the 3 cycles and the 5 cycles all fit in one conjugacy class in S5. But when we restrict to A5, we must check that, That if, for instance, there exists in the centralizer of the element, there is an odd element that we can always conjugate within A5. Okay, this was one exercise in the last sheet, you remember. Instead, if we look at the 5 cycles, the 5 cycles, if you take 5 cycles, 1, 2, 3, 4, 5, if we look at the centralizer in A5 of this, or even in S5 of these 5 cycles, it is only the subgroup generated by itself. So, and all the elements of the 5 cycles are even. So, we cannot conjugate all 5 cycles in A5. And in fact, we have 2 conjugacy classes. As you see, for instance, these two are conjugated in S5, but not in A5. There is no element, even element, what? Which one? These ones? Ah, then I took it from the 1, 2. Wait a minute, let me see if I made a mistake in copying it. Okay, now let's then just call it prime, and that's it now for the moment. Okay. Okay. 1, 2, 3, 5. Yeah, okay. 1, 2, 3, 5, 4. Okay. Okay, so we are safe. Okay, okay. Yeah, no, in fact, I copied it from the other notes. I didn't check it. Okay. So 3 cycles are in 1 conjugacy classes, 5 cycles in 2. Okay, now we come to question 4. And then question 4 will determine the dimensions of the remaining representations. So question 4 will determine, no implications, determine dimensions of row 5, row 3, and row 3, 1. So as we saw from the second last lecture of René, the columns of the character table, not only they are orthogonal with respect to the usual product, the usual scalar product, no, sum of products of the corresponding coordinates, but they also have the norm of these columns are equal to the cardinality of the centralizer of those elements. So if we take a column, Ci, the ith column, we have that Ci corresponding to the ith conjugacy class, then this is the norm of G over the norm, the cardinality of G over the cardinality of the conjugacy class, which is the cardinality of the centralizer in G of the element Si. Okay, so in the first column, what do we have? Who is the centralizer of the identity? It's the whole group. So the first column will have, suppose that here we have entries A, B, C. The first column, C1, will be equal to 30. And this means that 1 plus 4 square plus A square plus B square plus C square has to be equal to 60. So this is equivalent to A square plus B square plus C square equal to 43. Now, A, B, C are integers. I forgot to say that to be greater or equal than 2. 60. Yeah, sorry. Yeah, 60. Sorry. 60. So this is the equation that A, B, C must satisfy. A, B, C are integer and non-negative, but actually, in the case of A5, are actually greater or equal than 2. Let's show that they are greater or equal than 2. So we have that A, B, C are integer, are positive integers, and now let's observe that they are Why is that? ABC greater or equal than 2 means that only the trivial representation has dimension 1. This says that all representations of A5 are of dimension at least 2. And in fact, suppose by contradiction, let's prove this claim. Suppose that by contradiction that there is a non-trivial representation of dimension 1 of A5. So suppose let rho be a homomorphism from A5 to GLC, which is C star. So we have a homomorphism from A5 to an abelian group. And so it means that this homomorphism must factor through the commutator subgroup. So this means that the commutator subgroup A5 is contained in the kernel of rho. But A5, its commutator coincides with A5. So the representation is trivial everywhere. But let's see. But A5 commutator coincides with A5, and so rho is the trivial representation. So this tells us that ABC not only are positive, but are actually greater or equal than 2. So now we study these equations, these conditions here. And you see, the sum of the squares has to be 43. So ABC cannot be larger than 6, for instance. But if we take 1 equal to 6, A equal to 6, we get to 36. And then we don't make it with the other one, or we exceed 43. So if you study some cases, if you do a little bit of case study, you realize that the only solutions of these equations are A equal to 5, I mean, of course, up to permutation, A equal to 5, B and C equal to 3. No? So here we filled here with 5, 3, and 3. Cosa fa? Ah, here, sorry, yeah, sorry. Okay, excuse me. Oi, oi. Okay, so we have 5, 3, and 3. Okay, so at least we have cleared what the dimensions of the remaining representations should be. Now, let's see. Now, okay, let me see. Yeah, now we do points 5 and 6. Points 5 and 6 are some general considerations about presentations of finite groups, but as a consequence, we will be able to determine, to show, for examples, that the column 2 and the column 3 have only real entries. And then, subsequently, we can actually determine the values of those columns. So, now we do points 5 and 6. Okay. So points 5 and 6 will imply that column 2 and column 3 are actually real. So, do we have? We have G is a finite group. Suppose that the cardinality of G is n. If we have a finite group of cardinality n, Lagrange's theorem tells us that every element to the power n has to be the identity, right? So Lagrange tells us that sigma to the n is equal to the identity. But this also tells us that if we have a representation of G, any matrix representative of this element will satisfy the same, at least this relation, right? So in particular, this says that given sigma in G, the representative matrix A of sigma, any representative matrix of sigma will satisfy sigma to the n is equal to the identity. And this forces every eigenvalue of the matrix to satisfy a similar equation. So in particular, we have that for every lambda eigenvalue of a sigma, then lambda to the n is equal to 1. So every eigenvalue of a representative matrix of a finite group is a unity. So it's a complex number equal to its inverse. No? The conjugate is equal to its inverse. Not equal to, its conjugate is equal to its inverse. So this means in particular that lambda inverse is equal to lambda conjugate. Okay, this is a general remark, right? So, and now let's think, what is a character of the representation? Is a sum of all the eigenvalues of a sigma. So the character will be a sum of roots of unity. right, of nth root of unity. Of course, if the element sigma has order less than n, for instance, it can be more precise. More precisely, if the order of sigma is m, and m certainly is a divisor of m, then, in fact, lambda will be an nth root of unity. But this property is always valid, right? So, okay. Now, let's see. Okay. Now we have another observation, also general observation. And the general observation is that if sigma and sigma inverse are conjugate in G, then what do we have? We have that the character of V of sigma is then equal to the character of V computed in sigma minus 1. But we know that the eigenvalues of sigma minus 1 are the inverses of the eigenvalues of sigma. So then we have that this is because of the properties of eigenvalues that I mentioned earlier, this is equal to the character of V of sigma bar. No? This is because, so even the sums satisfy the same relation. So these are general considerations which now we apply to our case. For instance, you know, the column C2 contains the characters of elements of A5 which have order 2. So all the eigenvalues, so if we take a sigma like a 2-2 cycle, we have that the order of sigma is equal to 2. So the eigenvalues of sigma, the eigenvalues of a sigma, let's say, satisfy lambda squared is equal to 1. So they are necessarily 1 or minus 1. Right? So and so we can be sure that these entries here are real now. Right? So characters are sum of eigenvalues. Eigenvalues are either 1s or minus 1s. So in this case, they are not only real, they are real. Actually, okay. So here we have this is real. Now we go to 3 cycles. Let's observe now that also the third column has all real entries. You know, we have just mentioned earlier that all 3 cycles are conjugate in A5. So this means that since the inverse of a 3 cycle is a 3 cycle, this means that every 3 cycle is conjugate to its inverse. Now, if we take sigma in the class of 1, 2, 3 cycle, then we know that sigma and sigma minus 1 are conjugate. Hence, as we just observed, the character of sigma is real. Okay? Questions? Okay, so this is also real. Okay. Okay, now, now in fact, we use this orthogonality relation to determine C2 directly. Okay, so now I erase this. Now let's look at C2. It's like 0.8 and 10 enable us to determine C2, the second column. We just said that the second column not only consists of real numbers, but actually sums of plus or minus ones, right? So we use the fact that the second column has to satisfy C2 dot C2, this is the usual scalar product, equal to, we said, the order of the centralizer. So in this case, we get so the 4. So let's call R, S, and T the numbers which you want to determine here as T. We want to determine R, S, and T. In fact, and they must satisfy the relation of 1 plus 5R plus 3S plus 3T is equal to, what was it, 15? No, one moment. 4, we just said 4. 0, what? Come 0? This is with itself. No, this is the, aspetta, one moment. No. Ah, no, sorry, I made a mistake in copying. Yeah, sorry. Yeah. So we have to now compute C2 in a product with C2. So 1, 5R plus 3S plus 3T is equal to 4. But, no, sorry, R squared. Okay, the squares. Excuse me, one moment. So I have to compute C2 in a product C2. So 1 plus R squared plus S squared plus T squared. And this has to be equal to the order of the centralizer is the 60 over the cardinality of the conjugacy class, and in this case is 4. So, sorry. If and only if, then R squared plus S squared plus T squared is equal to 3. And then recall that R and S and T are plus or minus 1s. So, in fact, again, if you do some study case, also here you find that the only possibilities are R equal to 1, S and T equal to minus 1. Okay. And so we can complete the second column. No, sorry. Yes, but I need more condition. We also have that, for instance, together with this, we also had that C2 cross C1 is 0, but I think this should be sufficient because they are all ones and minus ones. Or no. This tells us that no, 1 plus. No, one moment. No, I erased too much. So C2 cross C1 equal dot C1 equal to 0. This is equivalent to 1 plus 5R plus 3S plus 3T is equal to 0. Now if we put these two together, then you see that R is equal to S is equal, R is equal to 1. So we put these two together, then we have R is equal to 1, S and T are minus 1, excuse me. Okay, no. Is it clear now? Yes, no, you need both, otherwise, okay. So we have here now, we determine R, S and T, and they are one, minus 1, minus 1. Okay. Now let's see what else. Let's give a name to the other entries that we need to determine. So the remaining ones that we want to find are U, V, W. Here we have X, Y, A, B, C, and D. No, we have to find the other ones. So now we apply those general principles that I mentioned earlier to compute the third column. Okay, now point 7 will help us determining U, V, and W. So, as we already mentioned, column C3 is relative to the 3 cycles. And we just said that in A5, 3 cycles are conjugate, and so the character of any representation on the 3 cycles is real. Okay, now you see the 3 cycles are elements of order 3. And the cubic root of 1 are complex numbers that in the complex plane they lie on the vertices of an equilateral triangle with one vertex in the origin, and here we have omega and here we have omega bar, which is equal also to omega square and omega inverse. It's okay. So if you have omega, here is e to the 2 pi I over 3, for example, we can choose this. And this is minus a half plus I times square root 3 over 2. Okay? It's a cubic root of unity. It's cos of this here. Okay, this is 120 degrees. Okay. Now, if you have the representative matrix of a sigma is, we said, as this kind of eigenvalues, and the character of sigma, for instance, in the 5-dimensional case, will be the sum of 5 cubic root of 1. And for the other two representation will be the sum of 3 cubic roots of 1. But you see, the cubic roots of 1, except 1, they have a non-zero imaginary part. So if we want to find a real value as a character, as we know, you must take sums that contain both omega and omega bar with the same coefficient, right? So, and the character will be something like alpha 1 plus beta omega plus gamma omega bar, but beta and gamma must be equal, otherwise we don't get a real number. So this, and now look, what is it? Omega plus omega bar. Omega plus omega bar is, what is it? Beta is gamma. No, okay, just a slip. Okay, and now, so it means that here we get something like alpha 1 plus beta omega plus omega bar. And now omega plus omega bar, it is twice the real part of omega. So this is twice the real part of omega. And the real part of omega, we just said, is minus a half. So here we get a minus 1. So the character will be a sum of minus 1 and 1, the other eigenvalue. So we get an integer. So this is an integer. So this discussion implies that on every 3 cycles, not only the character is real, but is actually an integer. So for every sigma 3 cycle, chi v of sigma will be an integer. Okay, so now we have then u, v, and w, real numbers. Now we must determine so now we have u, v, w, integers. And now we can apply the orthogonality relations that we know. Now let me see. So, for instance, we have we know that C3 cross C3 not cross dot C3 is equal to 1 plus u square plus v square plus w square, and this has to be equal to 3. Then we have C1 dot C3 is one moment. No, I missed the P1. No, C1, no. 1 plus 1, 2, 2. Here is a 2. No? 1 times 1 plus 1 times 1 plus u square, v square, w square. So this tells us that u square plus v square plus w square is equal to 1. That's one condition. The centralizer is order 3. Yes, 20. The conjugacy class is 20 elements, so 60 times divided 20 is 3. Then we have, we can use the fact that C3 has to be orthogonal both to C1 and to C2. So C3 dot C1 has to be 0, and C3 dot C2 has to be 0. So now we find that this tells us that let's see. Yeah, this tells that 5 plus 5u plus 3v plus 3w is equal to 0. And the last one tells us that 1 plus u minus v minus w is equal to 0. And also in this case, if you do a little bit of case study, you obtain that, in fact, u has to be minus 1 and v and w has to be 0. So this implies that all this imply that u is minus 1 and the two remaining are 0. Are 0. Okay. I have to finish. So now, for instance, we can points 9 and 11. Now we can complete row 3. Completing row 3, we just we answer to points 9 and 11, completing row 3. What do we know? For instance, we know that C3 and C4 and C3 and C5 have to be inner product 0. No? C3 dot C4 has to be 0, and C3 dot C5 has to be 0. So this implies that x is 0, and this implies that y is 0. So we completed the line here. So 0 and 0. So now we are left with these last 4 elements, which we should determine. Okay. Now, again, we can use the orthogonality relations, and so if we use the orthogonality between C2 and C4, we obtain that 1 minus A minus C has to be equal to 0. And if we do also C2 dot C5 is equal to 0, we find that 1 minus B minus D is equal to 0. So this tells us what? This tells us that C is equal to 1 minus A, and D is equal to D is 1 minus B. Okay. But it's not finished, because now we can use the fact that C4 dot C4 is equal to C5 dot C5, and they must be equal to 60 over 12, which is 5. So now we have 2 more equations that we can write. And of course, now we keep into account that C is 1 minus A, D is 1 minus B, and then we find the 2 remaining equations are, I write them here, are 2 plus 2A squared minus 2A plus 1 is equal to 5, and 2 plus 2b squared minus 2b plus 1 is equal to 5. What is this? Tells us that a and b are roots of the polynomial, if you just compute a little bit, x squared minus x minus 1 equal to 0. This is the degree 2 polynomial. And then the roots are, so we can just pick who is who. A and b will be 1/2 plus or minus square root 5 over 2. So now we can put them here. So, okay. 1/2 plus square root 5 over 2. Here we'll get the other one. 1/2 minus 1/2 square root 5. 1/2 minus 1/2 square root 5 and plus square root 5. So we completed the table. But maybe it's nice to comment a little bit on this table. You see, rho 3 and rho prime 3 are the three-dimensional representation, are two distinct three-dimensional representations, and their characters are the same on the identity, on the 2 cycles, on the 3 cycles, but the values, you see, are switched on the 5 cycles. And in fact, one has that the two representations are related by an outer automorphism of A5. So what we have is that rho 3 prime is equal to rho 3 composed with, let's call it tau, and tau is the conjugation by the 1-2 cycle. You see, this element sits in S5 but not in A5. So 1-2 lies in S5 minus A5. So it acts on by conjugation of A5. It leaves invariant, you see, of course, the identity, the 2-2 cycles, the 3 cycles, but flips these two conjugacy classes. And that explains why, you see, on this class, the character of rho 3 is this, and rho 3 prime, the character has the same value, but on the other class. So that makes them inequivalent, because you see, the two characters are equal up to a certain point. Here, this part are not equal anymore, but this explains why you have this symmetry in the values of the character. And one other comment is that the group A5 embeds in SO3 as the rotational symmetries of the regular icosahedron. And the regular icosahedron has how many edges? Oh, I forgot. Yeah, 30 edges, and these 30 edges contains 5 subsets of points, which are very special, no? 5 sets of 6 points which sit on the middle of an edge. So you have all these edges. You take a midpoint on every edge, and then you subdivide these midpoints in such in 5 sets, such that in each of these joining two midpoints in these 6 points, you obtain 3 orthogonal lines. And A5 is going to permute these configurations. That's the meaning of A5 inside. That's why. What are the 5 objects that it permutes? No? The icosahedron has I don't know how many faces, edges, and vertices. But who are the 5 what? And these 5s are these sets of 6 points, so-called orthogonal, because joining 3 pairs of them, you can obtain 3 orthogonal directions. And that, I would say, maybe I conclude here. I found a very beautiful note on the web, which I will put on the page of the course. I will put the link to that page. And then you find also some explicit matrices for the embedding of A5 in SO3. Okay? I think I concluded.